All right, well, good morning, everyone. Lots of light up here. Good segue, I guess, and tie into the new optics announcement and workshop that Alan mentioned later. So we'll be participating in that as well. And so I'll just make this a quick update or a review on what Quintessent's doing and quick updates since the last year. And again, thanks to Leslie and Alan for inviting me back. So at Quintessent, what we're interested in solving is the communication bottleneck between compute chips. As many of you guys know, compute chips themselves are getting better and faster, but the rate at which they communicate with each other and talk to each other has not kept up with the same pace. And so as a result of that, there's large system-level inefficiencies in how well computing power and resources are utilized that's hamstrung by the inability to move bits back and forth at high enough speeds, essentially. The fundamental challenges we run into if we try to scale existing solutions, and what I mean by that is predominantly existing Ethernet networking optics, to apply towards what I call optical compute interconnects, integrating them with compute chips to move data between compute chips and for specific workloads like machine learning and AI training, is that we find that if we just brute force take today's solutions and then try to scale them to move a lot more data, that we incur large penalties in any or all areas of unacceptable power increases, latency, size, weights, or increases in fiber infrastructure. And maybe the most important thing is if we look forward to the future, look towards applying optics towards computing for interconnects, today's technologies, I would say, are probably inadequate from a reliability standpoint for deployments. And if we envision a future system that has a lot more components, a lot more complexity, and maybe where the environment is less amenable to serviceability and replaceability. And so, this chart on the left shows a few different scenarios of reliability with different assumptions. And what we find by and large is, taking what is known for the reliability of common components used for optical communication today. And in this case, we're focusing on the specific, or the laser which powers optical communication links. We kind of fall short of what would be a common or a reasonable expected system level failure rates for an assumed total deployment lifetime of 7 years and for a 512 channel system. And so, those are the two challenges that we at Quintessent are trying to address and solve, basically summarizing being one is how to enable a new scaling curve for optical connectivity where the incremental cost to increase bandwidth is de minimis or negligible for the end user in both CapEx and OpEx, power, latency, et cetera, and also where the technologies themselves are reliable and can meet the threshold for what a total acceptable system level failure rate would be over the deployment lifetime. And so we think that requires a new fundamental change in paradigm in how we architect communication. I think we need to move to a wider and parallel architecture, in our case, one that uses many wavelengths of light that allows us to match to wide and parallel electronic interfaces to minimize the overall system level power and also optimize the bandwidth efficiency. And this then requires a new set of foundational technologies. And so for us at Quintessent, the ingredients for that are leveraging new advances in semiconductor laser materials. Specifically, we use what's called semiconductor quantum dots for our lasers and amplifiers for the generation of the lights and the lambdas. And that gives us an instant upgrade in efficiency, but more importantly, reliability. This material has been studied extensively at UC Santa Barbara, and they're known to have much higher intrinsic reliability than what is commonly used today to build lasers for optical communication links. The second is taking that material and then integrating it, heterogeneously integrating it with silicon photonics and silicon substrates, using silicon foundries for the manufacture of single chip solutions that combine the quantum dot lasers with other silicon photonics circuits and components to result in the simplest possible form factor, but also the highest possible reliability, eliminating and reducing and minimizing all possible moving parts. And there's other intrinsic benefits that this also brings to making the individual components on that circuit and the whole chip much more reliable. And then finally, we use what's called a multi-wavelength comb laser, and this is essentially a single laser, single device, but that emulates the performance of tens of different lasers. So we essentially get, performance of 10 for the price of one, and that's really critical for us in enabling our wide and parallel optical architecture, where that parallelism is enabled using lambdas. And really the key is, if we really want to unleash the power of parallelism in optical domain that uses many parallel colors of light, then there needs to be a way to simply and cheaply generate those colors of light, and we do that with the multi-wavelength comb laser. And so in the past year, we've been focused on validating and also optimizing the various fundamental components and technologies that go into, or in our suite of technologies. Lots of work that goes into optimizing the multi-wavelength comb laser. We've demonstrated some world record results in terms of output powers per wavelength and noise per wavelength. Some of the common questions we get around this architecture and this technology is, can you generate enough power per wavelength? Can you get low enough noise per wavelength to send data with high fidelity? And in the past year, I think we've answered that the answer to both of those questions is yes and yes. In Q1 of this year, we have announced with our partner Tower Semiconductor the world's first demonstration of taking quantum dot laser material and actually heterogeneously integrating it, combining it with a 220 nanometer silicon photonics process in the silicon foundry. And so this is now a manufacturing process that we can use to manufacture single chip solutions that combine the quantum dot laser with other silicon photonic integrated circuits for the full interconnect link. And then finally, very exciting to us a few weeks ago was we saw that the 2023 Nobel Prize in Chemistry went towards recognizing the general technology class of semiconductor quantum dots. And we were particularly excited to see that the work, or the description actually cites some work by some of our colleagues at Quintessent on quantum dot lasers. And so, at least someone else besides Quintessent thinks that quantum dots are an important technology class. So, and there's many other test chips that are currently in flight. What we're working towards is, again, optimizing those components and working towards building them together to now demonstrate link-level functionality. What we're the roadmap that we're working towards enabling is being able to build chips that can deliver data using anywhere from 8 to 32 wavelengths in a single fiber, being modulated at a range of different signaling speeds, for now up to 128 gig to match PCIe, and upwards of 4 terabits per fiber, very high bandwidth density, both edge and aerial, and very low powers. And one possible application of this technology is, if we look forward to PCIe Gen 7, what this technology could enable is a single chip that can deliver the full by 16 PCIe Gen 7 bandwidth, which is 2 terabits, over a single fiber pair, and only needing 1 or 2 lasers to make it happen, as compared to traditional alternatives today, where you might need 16 different fiber pairs and 16 different lasers, and so on and so forth. So that's a quick update. For more information, our VP of Engineering, Brian Koch, has given another talk in the workshop this afternoon on optical compute interconnects. And thank you very much.